Okay, so I want to talk about, we're going to go back to Laplace's equation now. So if you remember Laplace's equation, this just says minus Laplacian u is equal to 0. And typically we specify some domain, so like on the domain omega. And basically we're always going to assume that omega is a nice domain, meaning it's connected, doesn't consist of two different pieces. I'm also just going to assume things like the boundary is nice, like it's a smooth boundary or a piecewise smooth boundary, something like that. And it's open as well, meaning it doesn't contain the boundary points, but it contains the interior. Okay, so minus Laplacian of u is equal to 0 on omega. The domain itself, I include the boundaries and the interior, but I mean it is Laplacian of u is equal to 0 in the interior of the domain. Okay, so Laplacian of u is equal to 0 in the interior of the domain. It could be all of R2, or it could be some subdomain. Okay, what we're going to prove is the following fact here. Let me sort of draw a schematic here. Let's say this is our domain omega, and let's say we look at some point here. I'm going to call it x naught, y naught. I think that's slightly different notation than I have in the book or in the notes. And I'm going to look at any disk around this point of radius r. The only requirement on this disk is that it's completely inside omega. We don't want anything that's half outside of or part outside of omega here. Then what is true is that u of x naught, y naught is equal to the average value of u on that disk. In other words, it's equal to 1 over pi r squared times the integral over this disk, which I'm just going to call d sub r, just to have ease of notation, u of xy dA, and we're integrating in the xy variables. But there's more. Not only that, it is equal to the average value of u around the boundary of that disk as well. So if I look at 1 over, if it's a disk of radius r, the boundary is a circle of circumference 2 pi r, and we're integrating over the boundary of that disk. I'm just going to write it like this, u dr. Okay, so this is called the mean value property, and it's something that harmonic functions satisfy. It's a very important property. If you've taken a complex analysis class, basically everything is based on the fact that harmonic functions satisfy this property, because as many of you have noticed, or some of you have noticed in the discussion forums, the real and imaginary parts of analytic functions are harmonic. So this is one of the things that's sort of an ingredient to that. Okay, so now I want to prove why this is true. So I want to give a proof of why this is true. Let me see if I can give an outline for the proof. I'm first going to prove this and then use this to prove that. So I'm first going to prove this and then use that to prove that. And in fact, I'm going to show you how to go from this to that, but I think you should, once you see the proof, maybe you can figure out a way to prove that as well. Okay, so what I'm going to do is I'm going to define a function, phi of r, and phi of r is just going to be this integral here. It's going to be 1 over 2 pi r times the integral over the boundary of this disk, and let me remember I'm writing d sub r here, u dr like this. I have no idea why I put a vector there. That's not what I meant to have. And what I'm going to do is I'm going to prove that phi prime of r is equal to 0. So in other words, phi is constant. So what this means is that for any number, phi of r is equal to phi of 0. Though, what is phi of 0? I can't just directly plug in r equals 0 because I'm dividing by 0. So I mean the limit as r decreases down to 0 of phi of 0. Okay, so let's actually compute this now. So let's compute what this limit is equal to. So this is equal to the limit as r decreases to 0 of 1 over 2 pi r times the integral over the boundary of dr times u dr. Okay, now actually what I want to do is I want to replace, I want to not replace, but I want to switch to polar coordinates. What I want to do is I want to switch to polar coordinates. So I'm going to introduce a parameterization. I'll say r of theta, or sorry, not switch to polar coordinates, but I want to get a parameterization for this curve here and write out what this is as a line integral. So I'm going to say r of theta is equal to r cosine theta, plus x naught, r sine theta plus x naught. And so the magnitude, I'll let you figure this out on your own, magnitude of r prime theta is just going to be equal to r. Okay, so now I'm going to replace this integral with this, the parameterization. And when you do that, you're going to have the integral going from theta equals 0 to 2 pi, and then you're going to have u evaluated at this parameterization. So you're going to have u of r cosine theta plus x naught, r sine theta plus x naught times the value of the parameterization, or the magnitude of the parameterization, which is r times d theta. Okay, now I'm just in place here. I'm going to start making some adjustments. So notice what's going to happen. The r's cancel. Do you guys see that? The r's are going to cancel. So this r here cancels with this r. Okay, good. Well, one of the assumptions of the theorem here that I didn't say is we're assuming u is 2 times continuously differentiable. We're integrating over a finite interval here, so we have a continuous function over a finite integral. There's no problem in interchanging the limits, so I'm going to do that. I'm going to just put the limits there, but I'm going to have to erase some stuff. So this is 1 over 2 pi times the integral theta equals 0 to 2 pi times the limit as r decreases to 0. It's not so important that it's decreasing. I just want to point out that it doesn't go negative. That's one of the things that conceptually I want to have in mind here. Well, what's going to happen to this function as r goes to 0? Well, u is a continuous function, which means we can pass the limit inside the function here, and r cosine theta goes to 0 as r goes to 0. R sine theta goes to 0 as r goes to 0. Now I'm realizing there's a typo here. This should say why not. And this should say why not. Sorry about that. Okay, so now this is going to be, when I do the limit, it's just going to get u of x naught, y naught. So this is u of x naught, y naught, d theta. I'm going to move this over here. Well, now as far as u is concerned, as far as theta is concerned, this is now a constant. And so it's going to be an integral of a constant over length 2 pi, divide by 2 pi. This is u of x naught, y naught. Okay. I will actually say that the version that I just wrote it there is a little less complicated than what I have in the notes. All right, so now what I want to do is I want to prove this fact here. So what I've proven, so just to back up, phi of r is equal to this. I proved that I'm about to prove that phi prime of r is equal to 0. If phi prime of r is equal to 0, it means it's constant. In other words, phi of r is equal to this limit here. And I just showed here that that's equal to u of x naught. So in other words, I've just shown that phi of r is constant and it's equal to u of x naught, or u of x naught, y naught, which is exactly what I wanted to show. Now I need to prove this. Okay. So we can now turn to proving that. And like I said, for the Poisson's equation thing, we can do this in a way that I think is actually in some ways better than the way that I'm going to do it here. We can do this using the the two-dimensional divergence theorem, integration by parts, that sort of thing. But I'm just going to do it by switching to polar coordinates because that's kind of what I have in my mind to do here. Sorry, that's not a good reason. That's not the only reason that I'm doing it. The main reason that I'm doing it is because I think doing it in polar coordinates is a little more tangible, and then I suggest you guys think about how you can solve this. Instead of doing polar coordinates, do these same sort of things that we do, but instead of using polar coordinates, do it using the multivariable calculus versions of things like multivariable chain rule, multivariable divergence theorem, integration by parts, whatever you need to do this. Okay, yeah, so I will now compute the derivative here. So I'm going to compute the derivative. This is phi of r. I'm actually going to need this space here, so I'm just going to remind you, just say over here, that this is phi of r. And let me get rid of this. I haven't proven this yet, right? I need to prove that. It's true, but I need to prove it. Okay, so I want to get rid of that for now. But no, it's there. I'll put it in purple, knowing that it's there. And I'm leaving it as an exercise for you to prove that. It's also in the notes. Okay, so phi prime of r. How are we going to do this? Well, our variable appears in two places. And actually, before I even do this, I want to write this in terms of a parameterization. So I'm going to have 1 over 2 pi r times the integral from 0 to 2 pi u of r cosine theta plus x naught r sine theta plus x naught times the derivative of the parameterization, which is r times d theta. Okay, so I've got r in several places here, but notice that this r and that r are going to cancel. Okay, so this goes away, and that goes away. And now I want to compute the derivative. So now phi prime of r well, because, again, u is a continuous function and we're integrating over a finite interval here, I can put the derivative on the inside of the integral. And what I'm going to have the integral from 0 to 2 pi, and now I need to do the derivative of this with respect to r, which is going to be the multivariable chain rule. So what I'm going to do when you do that, if you go back through the videos where I talked about different notations on derivatives and stuff like that, one of the ways that you can write this is going to be the gradient of u, which means the derivative in the first component of u is a vector where the derivative is, where the first component is the derivative of u in the first component, and the second component of the vector is the derivative of u in the second component. So this is the gradient of u evaluated at the point r cosine theta plus x naught r sine theta. I did it again. It should be plus y naught. I don't know why. Okay, r sine theta plus y naught. And then we're going to dot with the derivative of that component with respect to r, which is cosine theta. And then we're going to dot with the derivative of this component with respect to r, which is sine theta. Then we've got d theta. Okay, sorry, I just found a more serious error in my notes here. Now, I want you to observe something here. So r of theta is equal to r cosine theta plus x naught r sine theta plus y naught, and the derivative r, which is the tangent vector, is going to be, so I'm taking the derivative with respect to theta, it's going to be minus r sine theta r cosine theta. This vector right there, cosine theta sine theta, that is the normal vector at the point corresponding to theta. And you can confirm that by doing the dot product of those two vectors, and it's 0. The tangent and the normal vector are perpendicular to each other. But another way to think about this is if you have a circle, this point right here is the vector going from there to there is cosine theta sine theta times the radius of the circle. So the vector going from there to there is cosine theta sine theta times the radius of the circle, and then so the normal vector there is just going to be the unit version of this vector, which is cosine theta sine theta. Okay, so what we have then, that vector cosine theta sine theta, this is the normal vector. So we're dotting with the normal vector. So we've got the gradient of u dotted with the normal vector. So we're almost in a setup for the one side of the divergence theorem. So if I multiply this by r, that is the magnitude of the magnitude of the tangent vector for the parameterization. If I multiply it by r there, I have to divide by r over here. But this is 1 over 2 pi r. Now we're doing the line integral of the gradient dotted with the normal vector. That's what this is. In other words, this is equal to the integral over this set of the divergence of this, so gradient dotted, not skipping steps. This is the gradient of u dotted with the normal vector dr. But the divergence theorem says this, it says this integral here, I had d sub epsilon, it should be d sub r, says that this integral is equal to the double integral of the divergence of the vector field, like that. And again, this is over d sub r. But remember, the divergence of the gradient is just the Laplacian. So this is the Laplacian. And that's equal to 0 because the Laplacian of u is equal to 0. So in other words, phi prime of r is equal to 0. Okay, like I said, this is one way to prove this. I think the introduction of polar coordinates was in some ways not necessary, but I think it makes it a little more tangible in some ways to wrap our minds around what's going on here. I would love to see, like in the discussion forums and stuff like that, if somebody could give a proof of this whole thing without switching to polar coordinates, and explain what's going on with various divergence theorems and stuff like that. Okay, but that's it for this video. This shows so this shows the mean value property, and I'm going to leave it up to you to either read in the notes or, even better yet, try to prove it yourself why this is equal to that. I would start to compute this maybe in polar coordinates, and then the phi of r is going to show up there. Okay, thank you.